Thanks for everyone coming to the afternoon session. Hope you're not too sleepy. Let's go ahead and begin. Greta is going to be telling us about the Kronecker coefficients of the symmetric group and complexity in combinatorics.
Thank you very much. Thank you very much for the opportunity to speak here at Simons once again about the Kronecker coefficients, but this time, hopefully there will be some new results and a slightly different point of view. And before I start with the talk, I must say that I don't see what's happening on Zoom, so we don't have this on the screens here. So if you have any questions and you're watching on Zoom, please shout out. Okay, so what is this? What's the story about? The story with the Kronecker coefficient starts with very simple combinatorial and algebraic objects, the symmetry group, which is just the group of permutations, which are just bijections from one n to one n, and we view them as a group under permutation composition. And then we have other major objects that are going to be used throughout the talk. These are the integer partitions, and they will show up in representation theory as weights. And they're highest weights. They are just integers, weakly decreasing sequence of non-negative integers that sum up to n, and we draw them with Young diagrams in terms of boxes. So what are representations? So they were mentioned already a few times implicitly. Let me just explain this very briefly so that we have some idea what I'm talking about. So the representations of, in this case, the symmetric group, and in general, there are group homomorphisms from this group to the general linear group, or in other words, ways of representing the group elements as matrices so that the matrices would obey the same rules as the group elements. And one classical way of representing matrices, for example, is the permutation matrix. So for example, this permutation 2, 3, 1 would go to this permutation matrix. So this is a representation. And once we have this construction, we want to know what are the invariant spaces, or in other words, how do we decompose it into irreducible? So the irreducible representations would be the minimal SN invariant subspaces, and they would decompose into direct sum our vector space. So for example, for this representation, we have that there are actually two irreducible representations. You can verify immediately that the vector space spanned by the vector 1, 1, 1, or these are the elementary basis vectors C1, E2, and E3. This is an invariant space, and here is the other one. And we have, this is classic, these are classical 100-year-old results that we know how to characterize these reducible representations of the symmetry group, and actually also of the general linear group, using exactly these guys, these partitions. And the reducible representations of the symmetric group are in one-to-one correspondence with the integer partitions of n, and in particular there is a way of identifying them, and the trivial representation is just one row partition, and this guy here is the partition 2, 1. So you should trust me. Okay. So a little bit more background before I can define the main players. The more background is, so the characters of the symmetric, this SN irreducible representations. If we take our matrix for each particular element, we can take the trace. And in this particular example, the trace is going to be -1. And for a given representation, the traces of the elements actually determine the representation uniquely, thanks to various properties, the orthogonality of characters and so on. So instead of dealing with the whole matrices of the representation, we can deal with the characters. So these are the character chi of the reducible representation indexed by lambda, evaluated at the conjugacy class alpha. So conjugacy classes in the symmetric group are given by the cycle type decomposition of the permutation. And they can be computed with a combinatorial rule, which is, however, from complexity point of view, is as horrible as you want, because this is an alternating sum over Murnaghan-Nakayama tableau, which I'll give you an example in a moment. And then, so it's -1 to the height of the tableau. So we have no idea actually how many terms here cancel and so on. And here is one example. This is a Murnaghan-Nakayama tableau, is just a way of cutting our tableau into ribbons of given lengths. So the lengths are the type of the tableau, the second partition. The tableau has to be weakly increasing along rows and down columns. And the height is determined by the height of these ribbons. And so in this particular example, there are two. So here are two examples. One case we get -1, in the other case we get 0 as a character. So in some sense, everything I'm going to say now can be combinatorially defined with these formulas, forgetting about the algebra, but this is not very helpful. So now once we have discussed, we have characterized the reducible representations, the next natural question is to study multiplicities. Multiplicities in the tensor product of irreducible representation. So I'm going to start with something that you're probably more familiar with, since so people work with the general linear group. The reducible representations are again indexed by partitions. This time the partitions are just have fixed finite length bounded by n, the size of these matrices. And if you take tensor product, like von Neumann started doing it and studying Lie algebras in the 30s, you can decompose this as a reductive group. So you can, the tensor product is still a representation that we can decompose into irreducibles with certain multiplicities. And these multiplicities, for given lambda mu and then nu, are these C lambda mu nu Littlewood-Richardson coefficients defined by Littlewood and Richardson in 1934. And they can be computed. So I'm stating this as a theorem in 1934, but it actually took maybe 20 or more years to actually prove that this is actually going to be the rule. So they are equal to the number of certain types of tableau of skew shape mu over mu and type lambda. Or also count integer points in a specific the Hive polytope. So this is another way of describing it. So this, I'm not going to go into the details of the rule, but basically you trust me that we're counting structures like this. And this is a Sharpe formula, if we want to put it in a complexity perspective. So, which is exactly what we have here. So if we have the problem LR, which is to compute the value of this Littlewood-Richardson coefficient, this is because of this rule, we can prove that this is in Sharpe. And if we want to decide whether the Littlewood-Richardson coefficient is strictly positive, so not equal to 0, it's actually a small miracle, thanks to the saturation conjecture proven by Knudsen and Tao, that this is actually polynomial. So the next thing one can do is take the reducible representations of the symmetry group and play the same game. So take this tensor product, we have the diagonal action of Sm, decomposes into irreducibles with certain multiplicity of each irreducible representation. What is this? These are our Kronecker coefficients. And so here are some examples. So this two irreducibles will decompose into each irreducible uniquely one. So each of these coefficients is going to be one. And it's already hard to actually calculate any bigger examples. Certainly, if you ask Sage to compute Kronecker coefficients, you're going to be out of luck after maybe N20 or something like that. And this is actually so another way to define them is going back to what Matthias Christendo was talking about in the quantum marginal problem, where you have this in the three dimensions tensor of these three spaces. By Schur-Weyl duality, it decomposes into general linear group irreducibles v lambda, v mu, and v nu, these tensors, and the coefficients, the multiplicities, are exactly the same Kronecker coefficients. So maybe so just to connect with Matthias, so they were interested in the moment polytope, which is for this problem boils down to figuring out if for a triple of rational coordinates, if you scale them large enough by some integer n, is this strictly positive? So inherently there is a problem already there about Kronecker coefficients, and here it's an explicit form like this. And of course, the last thing is where we can define them as an inner product of these characters I just described. So you can, in principle, with pen and paper, calculate the values of the Kronecker coefficients without actually finding the matrices, but I just said, but this is a horrible formula because, as we said, these characters are alternating sums of exponentially large objects. And so what do we know about computation of these quantities? So as I said, so the Littlewood-Richardson coefficients are relatively nice. The characters are basically as bad as you want, and we are in the process of describing exactly how bad the characters are. But just deciding whether the character is 0 or not is an NP hard problem. And the same thing holds for the Kronecker coefficients. Again, to calculating the problem given our input lambda, mu, and nu are figuring out if they are strictly positive. So for the Kron, we don't actually know whether this is in sharp P. We only know that's a gap P. So it's a difference of two sharp P functions. That's the best we know. On the other hand, we know there are no negative integers from the representation theory. So is this in sharp P or not? That's actually the big problem in the complexity world. And deciding whether they're positive is an NP hard problem, which is a recent result by Christian Ickenmeyer, Ketan Mulmuli, and Michael Walter. Okay, so in some sense, that's the complexity. So now what? Well, okay, so yeah.
I guess, are they, is it sharp P hard? Even if it may not be a sharp.
Yeah, it's a sharp P hard. So I'll give you some examples later. So Actually, I'll give you an example right now, which would explain why they're sharply hard. And this is really the example. So this is one slide of what's known from the combinatorial point of view. And people in combinatorics who were first studying these questions, they didn't phrase this in computational complexity terms, but we're asking, is there a combinatorial interpretation? So is there some nice way of nice discrete family of objects where we say that the Kronecker coefficient is equal to the number of these objects? This is what they wanted as a combinatorial interpretation, but formally it's exactly asking whether this problem is sharp P or not. And here is basically the proof that it's going to be sharp P hard, because for a very special family of partitions, you can reconstruct the Littlewood-Richardson coefficient. And the Littlewood-Richardson coefficient for another special family of partitions who can boils down to the knapsack problem, so it's sharp P hard. Yeah?
In all of these complexity theoretic results that you're stating, what is the precise sense of the size of the input?
So that's another very good question. So what I'm stating so far is going to be in binary. So these partitions lambda, mu, and u are sequences of integers which are encoded in binary. And in that sense, this is sharp P hard. However, with the Kronecker coefficients and the characters, we already know that even input in unary is giving us sharp P hardness. With the Littlewood-Richardson coefficient, this is not exactly clear. But hopefully soon will be. And yeah, so they would be hard in unary as well. So this is one reduction. And the other things that we know are only very special cases when. So the first result came. Okay, the first results came in the late 80s. So just when two partitions are hooks, which is then the third partition actually can be at most a double hook in these cases. So it's very, very restricted. And some other special cases, but overall, even the general case of having a two-row partition and two arbitrary partitions, we don't really know. Okay, so why do we care about this Kronecker coefficient? So one motivation already Matthias Christander told us about. So it has to do with the moment polytope and the quantum marginal problem. And the other motivation has to do with geometric complexity theory. And so this is always hard, but let's see if I can explain geometric complexity theory in one slide. And of course, I'm going to cheat because I know you guys know mostly what this is about. But so already Peter mentioned variance P and variance NP problems this morning. So these are polynomials which are polynomially easy to calculate with, let's say. So depending on what model of computation we use, either algebraic branching program or circuits and so on. So there's already a sequence of refinements. But roughly speaking, in a very informal way, these are the easy polynomials, and the VNP is the algebraic version of NP. So these are the difficult polynomials, and distinguishing these two classes, VNP and VP and VNP, boils down to distinguishing the determinant and the permanent. In what sense? In the sense that the determinant is a universal polynomial for VP, and the permanent is a representative, the permanent is VNP hard. So if we show that the permanent cannot be written, so this is, I don't know if you can read, this is quite small. So if the permanent, we are going to look at what is the smallest n such that the permanent can be written as a determinant of a n by n matrix with affine linear forms. So alpha 1, 1, x 1, 1 plus alpha 1, 2, x 1, 2, and so on. So then, yeah, so the permanent m, sorry, yeah. So permanent m. So n is going to be some function of m. The minimum one is going to be the determinantal complexity of this particular polynomial. And basically, VP versus VNP boils down to showing that that this n is not polynomial, is super polynomial in M. So VP versus VNP is n bigger than any polynomial of fixed degree in M. Okay, so now, okay, so what is the geometric complexity theory here? Well, so these polynomials, these particular ones, the determinant and the permanent, they exhibit symmetries by, as you can see in these expressions and the coordinates, we can permute the rows and the columns. And in general, the fact that all we care about is up to some affine linear combination, we can act with the matrices with the general linear group on these polynomials, and we are still going to be in the same class of functions. So we use this, and this is so basically expressing the permanent as this affine linear combination as the determinant of a affine linear matrix. We might as well take the orbits acting as with linear forms on these polynomials. So in this case, the general linear group in n squared of size n squared, because we have n squared variables. So don't be confused that there are inherent n by n matrices here, but we are acting on this on the variables of the matrix, so n squared. And then we can apply, if we can write this, then it means that the permanent is in the orbit closure of the determinant, and we can take orbit closures on both sides. And now we can talk about an algebraic geometric object. So comparing the orbit closures of the permanent and the determinant polynomial. And then we can look at the ring of, so the coordinate ring of regular functions on these orbit closures. And what the GCT program of Mulmulian-Sukhoni says that if this inclusion of coordinate rings holds, then we need to show that n is bigger than polynomial in m terms, and this would immediately disprove this, that this is the other way, that the permanent is a polynomially large determinant. So one way to distinguish these coordinate rings, which are pretty large, is by looking at their decomposition into irreducible representations. Again, so these are GLN squared invariant spaces. So they are GLN squared modules. So we can actually decompose them into irreducible GLN representations, just like if we want to compare two large integers, we can look at their prime divisors and see which if there is a prime number which shows up with different degree in one versus the other. So we can say that one number cannot divide the other if it has a larger prime factor of some kind. So the same thing is here with the reducible representations. So if we want to distinguish this, if we want to say that the permanent is not in the determinant, then we need to find some partition lambda, which is going to be called an obstruction. So for which this the multiplicity here is smaller than the multiplicity here. And if we show this for n bigger than polynomial of m, then we basically get that VP is not equal to VNP. So this is a constructive approach. So we need to find a partition for which this inequality holds, and then we get distinction. So this is the idea of the GCT problem. And now if we want to, so these multiplicities are pretty horrible, as you can imagine. Now, since studying them is hard, probably hard, we might as well look into whether this multiplicity here is actually 0 and the other one is strictly positive. So that type of very simple inequality. And this is going to be called the occurrence obstruction. And this was a easier conjecture in the Mulmulian-Sukhoni program in GCT, that there exists such occurrence obstructions that would show that n is bigger than poly m. And unfortunately, as you probably heard of, this turned out to be false. So there are no occurrence obstructions. And then we need to look for multiplicity obstructions, which means that we need to figure out something more about the sizes of this multiplicities. Yes?
What does this negative result depend on this particular embedding of permanent indeterminate, where you complete it with a diagonal of, if you had a different, I mean, I know that it does depend on.
Yeah, so basically,
if there's another natural embedding, maybe this negative result doesn't also.
So you are right, because so what I'm not saying here in this situation is that we are homogenizing by one variable to degree n. So maybe but the other, and the problem is that we are using the determinant as a VP model. So if you want to get rid of this, you have to use the iterated matrix multiplication and algebraic branching programs. Then you are not going to have this problem with the different degrees and the embedding.
That the Flansburg continuation?
Yeah.
It's a natural even
Yeah. So
there's
I'll
one
say,
natural embedding. There are many other natural embeddings you can consider. I mean, it's not necessarily you can just plug the permanent, I don't know, n over m times along the diagonal or something. There are many things you can consider, and
yeah. So if you do that, then you're gonna get different description. So this is gonna be different, but then this is gonna stay the same, right? So and you're right that the way we disprove it is we actually do use the embedding. So in that sense, we cannot disprove another permanent versus another model or different embeddings.
So then with the new version with the iterated matrix multiplication, like occurrence obstructions are still possible, or it's not ruled out?
It's not ruled out.
Oh, okay.
Oh, but okay, so with that particular, it's not ruled out, but with the iterated matrix multiplication, it's pretty clear that it's occurrence obstruction.
So is it proved as well that even with the iterated multiplication, it's also ruled out? Or
no, we did not. We didn't write it.
it's on the determinant side. I mean, take embedded permanent in a different way. I mean, just getting to it, the diagonal.
no, but there's no padding. You can just work with the permanent.
Yeah, we
Yeah,
did
you
it.
can work with the permanent without cutting, right?
Yeah, that's why-
that's one way of doing it. All I'm saying is that there are many ways of doing it. You can do all sorts of things. And using a particular embedding just says that via this embedding, you will not find.
Yeah.
Correct. This particular thing is a flaw of the embedding. I will explain.
Okay.
But in the other cases, so from what we have studied, so okay, so let me just say go closer to the punchline. So why I was talking about this Kronecker coefficient so far. So the Kronecker coefficients lambda, so there is this partition lambda here, and d are the two parameters. D is the degree of the regular functions, lambda, and then n to the d, n to the d. This is an upper bound for the delta, for the multiplicity in the determinant. And then this gamma, the multiplicity in this padded permanent, is there is nothing very special about it other than that only particular partitions lambda can show up, and we are just bounding it by the multiplicity in the whole ring of degree d polynomials in n variables, which is what this is in the end. And this is just the Platism coefficient. So we actually, all right. So one problem is going to be that this coordinate ring of the determinant is pretty large. So okay. Okay, so the first conjecture, actually, even before the one we disproved, was that instead of looking at lambdas which don't show up in the determinant, we can directly look at lambdas for which the upper bound given by the Kronecker coefficient is 0, and which show up in the permanent, and that such lambdas would exist, and this is basically what we first disproved, and this was just purely using combinatorics of Kronecker coefficients to the extent we actually know it, because as I said, so we don't really know that much about Kronecker coefficients to begin with. And in the course of the study, we actually used complexity theory and geometric complexity theory. We proved an inequality between Kronecker and Platism coefficients, which using representation theory is not at all obvious, because the Kronecker coefficients and the Platism coefficients are different multiplicities of different types of spaces. So there is no natural map between them or any other correspondence. Okay, so this is the full result that we actually we proved with Peter later, that if n is greater than or equal to m to the 25th, so basically we cannot prove a better. So this is the only lower bound we could prove with this GCT method, if at all possible. So we haven't really proved that. But for n greater than or equal to m to the 25th, basically, if some partition occurs in the coordinate ring of the orbit closure of the padded permanent, then it's also going to occur in the coordinate ring of the orbit closure of the determinant. And then we cannot prove a super polynomial lower bound this way. Okay, so let me tell you briefly what we did with the Kronecker coefficients without actually having a formula for the Kronecker coefficient. So what can we do? Well, it's not that we don't really know absolutely anything. So there are some tricks. But before that, let me just point out where this embedding is the embedding itself is obstructing the obstruction model in some sense, but this was actually as said, so a result of Landsberg, that if we look at this padded homogeneous polynomials, and it doesn't matter that here it's the permanent of size m, it could be any other homogeneous polynomial of degree m and m squared variables, then the only multiplicities that could show up are such that lambda 1 has many, the first part has many rows. And actually the majority, when this n grows, basically what's growing is the first part of lambda. It's not anything else. And then also the length of lambda is determined by the number of variables that are used in this polynomial. So this is m squared. And also, if we are interested in this inequality, then we need to look for a large degree polynomial, so the bigger than n over n. And then once we have these types of conditions, then we can show that just already for n bigger than 3 m to the fourth, we already have a positive Kronecker coefficient everywhere we would care about for these types of partitions. And the way the proof goes, and similar in a similar fashion it goes for the other, for the bigger result, is that in order to prove positivity of certain multiplicities, we rely heavily on a few properties. So we rely on the fact that we know that the Kronecker coefficient of square, square, and square is greater than 0, and actually, there is a more general result. So if we have a Kronecker coefficient of two partitions which are symmetric, so self-conjugate, this is going to be greater than or equal to the absolute value of the character of mu, and then the main hook. So it's a particular character evaluation, and while the characters are bad in general, in this particular case, it's this character absolute value is just 1. So we have some other nice properties that we can conjugate to partition. The Kronecker coefficient remains the same. And then a third property for some special, so we can prove that if we take a Kronecker coefficient with some particular, so hook, and then a little bit any type of smaller partition here, as long as this is positive for some small value, small partition, is going to be always positive. So with the rectangle, and then basically we use this decomposition, the various positivity rules for smaller building blocks, and the semi-group property, which tells us that the Kronecker coefficient is of the sum coordinate-wise sum of partitions is greater than or equal to the maximum of the two the Kronecker coefficients of the first triple and the Kronecker coefficient of the second triple, as long as both are positive. So we can't just start from nothing. So it is, and in that sense, our partitions, we can cut them up in various squares and hook-like things, and then we can also cut up the rectangle in various different ways, compose it, and we get positivity. And just briefly to tell you the other result that I promised, how to use the geometric complexity theory to prove the inequality between Platism and Kronecker coefficient. So this is, the Platism is just the multiplicity of lambda in the symmetric d power in the symmetric n power. Or in other words, this is going to be the multiplicity of lambda in the coordinate ring of the orbit closure of all polynomials of n in n variables of degree d. So this is, and the other one is the Kronecker coefficient, which is described in terms of the symmetric group representation, but is also an upper bound for the determinant orbit closure. So we have this inequality between these two different types of quantities. How does it work? Again, so in this inequality holds when the first row is growing. And so basically, if this is our partition mu and our partition lambda is adding d times n minus m boxes, so this is going to be the big partition lambda. When we do this, not many things change. That's basically the idea. First of all, so there is again the Kadish-Landsberg result. Basically says that if we look at this orbit closure, Vm is all polynomials in m squared variables of degree m, then almost by definition, this is going to be greater than or equal to this Platism coefficient. We also have certain stability results. So when we keep increasing the rectangles and just adding partitions to just adding squares to the first row of the partition, we eventually it stabilizes. And now comes the complexity theory. So basically the complexity theory, geometric complexity theory tells you that if the multiplicity of lambda here is greater than the Kronecker, which is now greater than the multiplicity in the determinant orbit closure, it means that something here, some polynomial here cannot be represented as an n by n determinant of affine linear forms. So this space is larger than what you can get with determinants of size n by n. And this means that there is some polynomial with these properties over here for which the determinantal complexity is bigger than n, because n is the size of the determinant. Okay, so, and now we just argue by contradiction. So if our Platism coefficient is bigger than the Kronecker coefficient, then in particular, it means that the multiplicity lambda in this ring is greater than the Kronecker coefficient, then bigger than the multiplicity in the determinant ring, which is this delta, which means that there exists some polynomial of degree m and m squared variables, which has determinantal complexity bigger than n. But we know this stability is telling us that we can take n go to infinity, and we always will always find a polynomial with determinantal complexity bigger than arbitrarily large n, which is not true because we know these are polynomials of degree m and m squared variables. They can be computed with whatever, m to the m squared at most operations or determinant. So determinantal complexity is actually bounded for these polynomials. Yeah.
By monomial, a monomial in all variables of the base. Like it's 1 to n over n times 1 to n over n or something like that. But you still get that. Very simple embedding in which you don't just use one variable of them.
So then,
in a balanced way.
then you're probably modifying the weight, the lambda, by adding some other parts. So it's yeah, I mean, it needs to be proven. So I just the same by intuition that we don't exactly know, but we in some sense, we can track how the lambdas change. And
Well, then you will not have just one long row, you
Yeah.
have maybe m squared long rows, and I don't know if you can handle it.
Can you encode that embedding? And like you're saying, you're worried about using other embeddings. If you use other embedding, could you write it as a permanent with the padded embedding of something larger?
I don't know.
It just seems like then you could be sure that you don't
Yeah,
have to
if
worry
you
about
could,
that.
then maybe you, yeah, I don't.
I mean, okay, so in some sense, we are not using that. Well, we are using the fact that the embedding is of this form, but there is nothing specific about the permanent that we use beyond this point. So everything else that we do is on the level of the determinant and seeing of what things can be represented with an n by n determinant essentially. And,
So there is no obstruction, even if the polynomial was not permanent, but was just a monomial.
yeah, I mean that's.
Yeah, so that's something.
Yeah, that's so the fact that it's the permanent over there is not crucial here. Okay, so let me. Okay, so. So the Kronecker coefficient, as we were just saying, so they go with the characterization and the determinant. Now, if you're asking for different types of computational models, let's say iterated matrix multiplication and so on, you can still apply this paradigm, and you're gonna get some multiplicities which are upper bounded by various combinations of Kronecker, Littlewood-Richardson, and Pletism coefficients. So in any case, they will still show up, and in that sense, it's still important to see how large these Kronecker coefficients can go. And now, let me just tell you a little bit about the optimization part. So if this is a workshop on symmetry and optimization, where are the optimization questions? So the first thing, here we have a very easy combinatorial problem. Count the number of partitions which fit inside an L by M rectangle. And obviously the size of the partition goes at most up to L times M. These are the generating function is just the Q binomial coefficient. And it's actually a pretty hard theorem of Sylvester using Lie algebras to show that to prove that these numbers are unimodal, so weakly increasing and then decreasing. And the whole issue comes from the restriction inside this rectangle. If you just try to prove it simply by adding boxes here and there, you'll see that it's not so easy. So what this has to do with the Kronecker is this identity is that the Kronecker of rectangle, and just two rows. So we're again back to that setting we were studying for the determinant rectangle and rectangle. And this is just the consecutive differences between these numbers that show up here. So in particular, because the Kronecker coefficient is non-negative, you get an inequality between these numbers. And using properties, the semi-group property of the Kronecker coefficients and this character bound, we were actually able to show that these differences has this exponential bound. And later, we actually, with probabilistic methods, we were able to study this difference independently. So we actually know exactly the theta asymptotics for this particular value. So this is maybe the only instance of non-trivial values of Kronecker coefficients where we know the theta asymptotics. And here, what comes here is something pretty horrible. So I'm not going to go into details, but there is an answer to that question. And now from then on, what can we say? we can start with the most general question of what are the maximal possible values that the Kronecker coefficient can take, or Littlewood-Richardson for that matter. And this is a theorem of Richard Stanley, that the maximal Kronecker coefficient, if we go over all possible triples of partitions, is on the order of square root of n factorial. And the maximal Littlewood-Richardson coefficient is exponential in n. And now the question is, can we find for which partitions lambda, mu, and nu these maxima are achieved? So can we actually show any non-trivial lower bound? So we looked at this problem a little bit, so we can say something, and this is that if the Kronecker coefficient is gonna be large, then these partitions will have to have a very specific shape in the limit, and this is shape that looks like this, essentially. So this is what we call the Vershik-Kerov-Logan-Shep limit, which is the typical partition which we get under the Plancherel measure, or in other words, weighted by the dimension of the irreducible representation. And in that case, so this is that the number of standard Young tableau, or this is the dimension of the irreducible representation also. This is actually on the order of square root of n factorial, and then you have some compensating factor of this order of square root of m. And we know that partitions which have a large dimension, so the representation has a large dimension, they are going to be close to that shape. So this is basically the theorem has two parts. First, suppose that we have a sequence of partitions which goes to this very large, the largest possible value that the Kronecker can have, then these partitions will have to have this shape. And on the other hand, if we have two such partitions, then there exists a third one such that we can find a large Kronecker coefficient. But which one exactly? No idea. And again, so in terms of the maximal dimension, we actually have various types of bounds, which is where we get this theorem from. So what other bounds can we get? And so here is a bound that looks pretty large. So depending on which regime we use for the sizes of the partitions, then this bound can be meaningful. So for example, in this case, we have a small number of rows, but still not, so certainly not constant. And so for example, in this example, we basically have L by L squared, and our total size is just L cubed. And in this case, we have an exponential upper bound, so not the square root of n factorial that I was showing earlier, which is much bigger. And since this is workshop on optimization, let me just tell you very briefly how we prove this. And we prove this using contingency arrays. So contingency arrays are, in this case, three-dimensional. So these are three-dimensional arrays, so three coordinates I, j, and k. And the marginals, the two-dimensional marginals are going to be given by the partitions lambda, mu, and nu. So again, it's similar to what Matthias was talking about. So this is a marginal problem on these arrays. And then we have this identity. So if we sum over all lambda mu and mu Kronecker coefficient, and then this, so the Schur function, you can think of just the reducible GLM representations, and these are gonna be the characters, but in any case, these are polynomials with positive coefficients, so that's all we care about. Then this is the generating function for this contingency arrays when we write this in terms of monomials. And now we just expand this into terms of monomials. As I said, here we have positive monomials. Then we are gonna get that the Littlewood-Richardson coefficient is bounded by the number of marginal problems or contingency arrays. And now for them, we apply the asymptotic results that Sasha Barvinok developed for counting contingency tables, and for these three-dimensional contingency tables with given marginals, this number is upper bounded, or the logarithm of this number would be upper bounded by the maximal of this function, which is a concave function over this polytope over here. So we can find some maximum, which is depending if we take symmetric marginals. So if all these lambda, beta, and gamma have the same values, and we know that the maximum is going to be in the middle, and we can at least calculate this limit. And there is for in terms of lower bounds, we have some few strange examples, but very far from anything explicitly close to the exponent. And this is where I will stop since I'm out of time. Thank you very much. Yes.
This combinatorics of those contingency tables, there are some log concavity results. Do they enter the proofs?
Sometimes it's the other way around. We can prove some log concavity results using that.
What about, there are no results in opposite? Say you prove log concavity using more algebraic or like some polynomial ideas like hyperbolicity or whatever, and you transfer that result to that setting. Something like that exists?
There may be, but so we haven't applied it, so you should maybe tell me more what kind of results there are, and I'll see if it gives us anything. Yeah. So, but then, so definitely it's the study of this contingency tables is very related to all of this. It's still quite difficult. Yeah.
Other questions? Online audience, anything? I am wondering what do you think could help at all to get a sharp peak formula for the Kronecker coefficients using this contingency table description?
I mean, this is the thing that I've been using all this time somehow, and when the problem with the contingency tables is that the formula you get in the end for just a single Kronecker coefficient is still an alternating sum of the contingency array. So it might be better than the characters, but still you have to find some involution for these contingency arrays to cancel it, and there is no site to follow, no way of doing this as far as we know. But it's not an approach we have this proof. So
Other questions? Oh, I do have one more thing I was wondering. If I remember, there's still like a kind of approach using the actual highest weights for coming up with obstructions. Do you think that problems related to these ones still could arise there, or Do you think that that's more helpful?
So what do you mean then to use,
I mean,
to just construct something?
to construct, I guess, like an actual polynomial on which the orbitals.
Yeah, okay. I mean, sure, so if you can do this, but it's very hard. It seems to be harder than just finding the spaces.
Oh.
Where to.
I actually have one more question. In this VP versus VNP, have somebody tried with yourself to use another VNP, like functions, say Kelly determinant of rank with four indices?
No, this would be very interesting.
Because that was my idea, like was
Yeah.
because that is VNP also,
Yeah,
and it has more interesting structure and
okay, again.
But I know that you used that Kelly determinant for something.
I personally did not, but maybe
Yes,
it is
yeah.
okay. So,
Oh, okay.
but okay, yeah. So we should discuss this. So
If there's no more questions, let's thank Greta. Yeah.